When you connect to any website around the world, there's a really good chance your connection is going to use TLS, Transport Layer Security. Thanks to the magic of certificates and public roots of trust, we can validate as a client that our server is serving the site they say they are, and with modern versions of TLS, we can encrypt our connection with perfect forward secrecy. That's pretty much the gold standard of security. We've got strong AES or SHA-256 encryption on the wire, we've got perfect forward secrecy with our key exchange, and we're validating the other side of the connection using strong public key cryptography. So now the question is, why don't we do that for the other side of the connection too? What about authenticating the client to the server? Most of the time, the client authenticates to the server with a username and a password, which is a pretty terrible way of going about things. So today, I'm going to change that with Mutual TLS. Most of you are probably relying on something like a VPN if you're exposing services from your home lab. But that doesn't scale. If you want to let other users access your website, it can be pretty hard to have them join your VPN every time they want to do it. This causes hassle with their DNS servers. They might only be able to have one VPN connection at a time if they're on a mobile operating system. If we had a better way to authenticate our clients to our server, we could safely expose that to the internet directly without any sort of protection in front of it, relying on the cryptographic guarantees we get from Transport Layer Security. And that's exactly what Mutual TLS does. It brings the strong cryptographic key exchange and authentication we already have for authenticating servers to authenticating clients. So if that sounds good to you, then come along on this adventure. This video is brought to you by the ProtoArch XKM01 case-up. Now, as you guys know, I mentor some student robotics teams, and when I go to their robotics lab to mentor them, the two big things that I focus on a lot are software programming and computer-aided design, or CAD. Both of those are done on the computer. So it's not uncommon for me to get out my own laptop in the lab and show them examples of programs or CAD models, and we can work collaboratively to learn how to use both of these tools. Now that, of course, means I need a setup that's portable that I can take to the lab that's good for working on CAD, which means I need a real mouse. The ProtoArch case-up combines a Bluetooth wireless keyboard, a wireless mouse, and a handy laptop stand, all in one portable carrying case. Easy to store in my backpack and get out when I need it at the lab. Now the keyboard unfolds for a full keyboard layout, including a numpad. It can be paired with up to 3 devices at once. You can switch between them with the easy orange keys, 2 Bluetooth and 1 USB dongle. The mouse is similar. It can also be paired with 3 devices, 2 Bluetooth and 1 dongle, and it includes a little pocket for the dongle in the mouse as well. And hiding in a small pocket on the top is the stand itself. This thing unfolds into an adjustable laptop stand, which helps you prop the laptop up higher so you have a better line of sight when you're working. In my case, I'm often also standing up, or the people I'm working with are standing up. So we're looking at a laptop that's higher up than if it was down on the table. Of course, when I'm done working, it's really easy to fold it all back up and put it back in the bag for the next time. So if you like to work on the go with your laptop, maybe the ProtoArch XKM01 case-up is for you. Get it at the link in the description below. So first, a bit of fundamentals on TLS encryption scheme, and key exchange. So in Transport Layer Security, especially in modern versions with perfect forward secrecy, we will always have 3 different types of encryption that we're using. So first off, we have to actually encrypt our data. Now this is done using a symmetric key stream cipher. So what that means is both sides of the connection agree on what the key is. They use that key to encrypt all the data they send across. Now most of the time we use one of 2 ciphers for this, either SHA-256, which is a stream cipher, or AES, which is a block cipher, but we use Galois counter mode to convert it into a stream cipher. So now we have a way of securely encrypting all of the data that goes across the connection. But we somehow have to get those keys on each side. We can't just send the key over the internet, because then anyone who's listening could listen to our key and decrypt all our data. So to generate the session key, we use a method called ephemeral Diffie-Hellman, or ephemeral elliptic curve Diffie-Hellman, which is where both sides can essentially generate random numbers, send parts of the random numbers to each other. I'm not going to go into how Diffie-Hellman works, but here's a good video on that up here. Or maybe a link down below, I'm not sure yet. So with the ephemeral Diffie-Hellman key exchange, we've generated essentially a random session key that both sides know. Now, early versions of SSL tie to the session key to the certificate used by the server. And this was bad because if someone were to leak the server's key in the future, they could go back and decrypt past sessions. So with Diffie-Hellman, that's not a problem anymore. But we still need to authenticate the server, and optionally the client. And we do this using public key cryptography, specifically digital signatures. Most of the time, these will use either RSA or, again, elliptic curves. So in asymmetric public key cryptography, one side generates a private key and keeps it private, and then from that private key, they generate a corresponding public key, which they share out to the world. So if you're in possession of some node's public key, you can encrypt data using the public key that only they can decrypt. And likewise, if they would like to prove their identity, they can take a piece of data and sign it using their private key, and you can verify that signature using their public key. So those two properties allow us to create a key exchange where the client can validate that the server is in possession of the private key corresponding to a public key. But how do we know we should trust that public key? And that's where chains of trust come in. See, the server doesn't just provide a bare public key, they provide a whole certificate. And that certificate includes the public key. It also includes the SAN, or subject alternative name, which is basically the domain name of the server, dates like the date it was signed, how long it's valid, or the date it expires. And most importantly, that whole certificate is signed by the private key of someone else. That's our certificate authority. So the certificate authority has attested that this server is authentic. And if we trust the authority, then we can probably trust the server too. And there's not that many authorities in the world, probably less than 100 or so. And all of the major browsers, it's called the CA Browser Forum, have agreed on a list of certificate authorities that are part of the global trust. So Microsoft, Apple, and Mozilla essentially are administering these directories of the highest certificate authorities in the world. And if you fall down the chain from those, you'll be trusted as well. But how do we handle clients in that case? Well, just like the server, the client needs a private key that it keeps private. It needs a public key, which is signed into a certificate by an authority, and the server needs to trust the authority from the client. Now, the server certificate and the client certificate are unrelated to each other. They can use different key algorithms, they can be signed by different authorities. And this is important because we can have our server certificate signed by a public authority like Let's Encrypt, but then we can create our own private authority just for our clients if we want to. And just like a server, our client certificates will have a SAN, or subject alternative name. And this can be whatever we want. It could be a domain name of a computer if we're having two servers talk to each other, for example. Or we could make it, say, an email address, so user@domain name. That's another common construct for user certificates. We can also bind these certificates into a hardware key, such as a trusted platform module on a laptop or a YubiKey, if you're really into enterprise security. And that'll give you some really strong guarantees that the user is on the computer they say they are as well. I'm not going to do that in this video, but it's very possible and very easy to do. So now it's time to generate a user cert for testing. Now normally we generate a certificate authority, and that certificate authority is kept offline, somewhere safe and special. Then we generate a shorter-lived intermediate authority, which we use for online key signing. This would be like my YubiKey that I set up in a past video. This had an expiration of a year, even though my root had an expiration of 69 years. So I could sign shorter-lived client certs using my YubiKey on a day-to-day basis. Now if you've set up a certificate authority in one of my past videos, like this one up here, you can go ahead and use that. And I have links down in my blog post in the description on how to use small step certificate authority to generate these user certs. But just for the purpose of this video to get you guys up to speed, I'm going to generate a really simple certificate tree using OpenSSL. So here's the commands we got. So first we need to generate a root. So I'm going to do a two-layer where I have a root and then I have the end certs. So my root key is going to be kept on a server somewhere, and I'm going to use it to sign client certs. It's not ideal for security to have my root key just hanging out, but again, this is a home lab test. If you want to do something for real, you should probably use the small step CA that I set up in a previous video. I've decided to use SEP 384 for its high security. For my root, it's valid for 4 years. You can set the options however you want. So I set the country as US, organization is me, and we're just naming it test. I've also added a constraint that path length is 0. So no other certificate authorities can be below us. This is the lowest certificate authority. Let's go ahead and run that. So we generated our key. We signed it. It's valid for 4 years. Its name is test. It's ready to go. So next we need to generate the client cert. So we need to start by generating a private key, which we do in this case from the Activity 6 curve. It's a little bit easier computationally. Then we're going to generate what's called a certificate signing request. And this is signed by our private key, and it asks the root to please sign it. I've named this guy Adventure, so this is essentially the username that will show up in Mutual TLS. And I've set it to be valid for server auth and for client auth. Slight side note here. I'm signing this for server auth and client auth, which is how most TLS certs are signed. So even for servers that are just using server auth, most of their certificates are also valid for client auth as well. And Let's Encrypt does this by default. So if you have a bunch of microservices that are talking to each other that already get their server-side certs from Let's Encrypt, you can use that same certificate for client-side auth when you're acting as a client to connect to other services. So this might really simplify your infrastructure if you're into that whole microservices lifestyle. So next, we have the CSR. We need to sign the CSR using the root certificate, and then you can view it if you want to. Then I'm going to package it up into a P12 archive, which includes both the key and the certificate, so the OS can import it. Now, if you wanted to, you could just do this part and this part on the client and do these parts on the server. And that way your key would never have to leave the client, your client key. But in this case, we're going to encrypt the P12 file and then email it. Email is, of course, not the most secure key distribution mechanism, but again, this is a Homelab demo with a basic CA setup. If you're doing this for real, please watch my small step video. So go ahead and paste in the instructions. And now it's asking me for the password to encrypt the P12. And I should have a P12 file. So now we got a P12 file. We need to copy just the P12 file to our client. We can get rid of the CSR, the cert, and the key. And then we need to keep root.key and root.pem for later. So now I've copied the P12 file over to my desktop here. It's obviously not my real desktop, but you get the idea. So I'm going to go to my Firefox settings, search for cert, and I find view certificates. So here we have all the different types of certificates. We have the trust list that's built into Mozilla. This is used by most of Linux. We also have your certificates. These are mine. And I'm going to import a new one. So I'm going to scroll down and hit import. We pick that P12 file. Now we need to enter the password. And we're good. So it's a software security device because it's not hardware bound. We need the expiration date, all that good stuff. We're good. So now at this point, I've generated a certificate authority. This is what I'm going to use to trust all of my servers. So my servers are going to trust clients that come from this authority. Then I generated one client certificate using that authority, sent it to a P12 file, encrypted the P12 file, sent it over to my Ubuntu machine and installed it there. You would do that process for every single client. You're going to generate a new P12 for that client with the client's name as the common name. Then you're going to give it to them. They're going to install it in their operating system. Every operating system has support for this. It's built into iOS, macOS, Windows, Linux. It's everywhere. If you have that P12 file, I'm sure you can find instructions on how to install it. On like iOS, you just double click on it. Same with Windows, you just double click on it, it opens, installs it on Windows. Firefox has their own trust store, which I used here. It's pretty simple. So now let's go ahead and set up the server side of this. How does the server trust the client? So now that I have a working CA certificates, I'm going to show you how to set up Caddy to validate these client certificates. So here I got Caddy, it's working. This is just the example site that comes with it. It's on a website called testcad@appleware.net, and it's got a certificate. So it looks like it's using a cert signed by Let's Encrypt E5, so that's nice. For these tests with both Caddy and Nginx, I'm going to get my server-side certificate from Let's Encrypt. This is what I recommend you do as well. Let's Encrypt are another one of these Acme providers. As I said earlier, our client cert and our server cert can be from different certificate authorities. That's not a problem at all. So this is what my Caddy file looks like. I just set my email. And also, please stop using my email because I'm sick of getting you guys the renewal notices. But it just says root and file server. So we need to add in the stuff to configure Mutual TLS. So I downloaded root.pem for my certificate authority. I'm going to put it in the etc Caddy folder because that's where I need it. Now for the Caddy file, I have some examples on my website here. But we basically need this TLS section, and in TLS we need client auth. And in there we have a mode we can choose from. So in this mode I've set require and verify, but you can also set other modes. So as the name suggests, require and verify means we tell the client that it must send a client cert, and we verify that cert against our trust store in Caddy. And if either of those checks fail, then we kick out the client, we just disconnect. So it won't even hit our web server backend, it just get terminated by TLS. Now other modes you have are request, where we ask the client nicely but don't require it, or we could request and verify, or require but not verify. I don't know why you want to do that, but those are all options. So for example, if you want to have clients that use Mutual TLS skip some login page, you could do request and verify. So if the client sends one, Caddy will verify it, and regardless, it'll pass that information on to the backend. We also need a trust pool. So you could use the system trust store if you're using publicly issued certs. In this case, I've set up a file, and here's the PEM file. If you like using Caddy snippets instead, I wrote a Caddy snippet here. If you'd rather use the snippet, and then you can go down and import the snippet. So that's there. Let's save. So now when I come over to my test site, I get this error in Edge. Did not accept my login certificate. That's fun. Over here in the test system, though, it's requested I identify myself with a certificate. So I can choose from my certificate list. I only have one in this system, so I can choose this. Remember that decision. So it's showing me my certificate, adventure.applehour.net, etc. Let's go. And it works. So that is all it took to set up Caddy with Mutual TLS. Caddy is now requesting a cert from the client, it's disconnecting the client if they don't provide one, and it's validating that cert against the certificate authority that I provided to it. Now I can issue more certs from the certificate authority with OpenSSL, give them to my users, and they will be able to securely log into my website. Of course, Caddy is a reverse proxy, so you could use it as a reverse proxy for any of your backends if you want to. It'll protect them from unauthorized access. So this isn't just like a login page. They're not even making it to the login page. They have to provide a cert before they get there. So that's a pretty good first layer of defense, even if you still want to give them a username and password. For those of you who are big fans of Nginx, here's the Nginx config. So like in Caddy, it's not that hard to set up client validation in Nginx. Here we have three options: off, on, or optional. If we set it to off, then it doesn't request a client cert and we're fine. If we set it to on, then it requests a client cert, and if verification fails, then it returns a white web page that says 400 bad request. Nginx. That's probably not a page we want to be sending back to our clients, but it's what it does. If we set it as optional, then it will request the cert from the client and validate that cert against the CA, and then it'll just store that response, whether or not it failed validation or not, in a variable we can use as we're parsing the config file. Now, one of the downsides I noticed is that if the client connects over HTTP instead of HTTPS, they never do this check and they never get disconnected. So in my setup, I have two server blocks. One of these is port 80, and it just says 301 to wherever you came from. So this you could just use for every single one of your servers. It just says go to HTTPS. Then this one only listens on 443, so it won't have to deal with insecure connections. The other thing I did to deal with the 400 bad request was actually use optional mode here, so it will validate the cert, but it won't disconnect them. And then down here I say if they fail to validate, then disconnect them, return 444. 444 is a bit of an Nginx magic code. If Nginx returns 444, it actually just drops the connection immediately. It doesn't actually send anything back. So here if I try to go to my test setup, it gets kicked up to HTTPS, but then it says refuse to connect. But up here it has requested you identify yourself with a certificate. So I pick my certificate, say OK, and I've got the Welcome to Nginx page. So hopefully this config snippet for Nginx will help you build your own Nginx configs. I mean, there's obviously a lot of other web servers out there, more than just Caddy and Nginx, but I'm hoping this is a good enough overview for you to get started. So I hope this video gave you a bit of an understanding of Mutual TLS. I'm trying to emphasize that there's more ways to do security than just something like VPNs or Cloudflare tunnels or zero trust network architecture. And it's completely possible to build out a fully secure system using TLS. Now this of course assumes your application's already relying on TLS type traffic. That could be HTTPS, but actually TLS can secure a number of different protocols now, and this would apply equally to all of them. So there's also plenty of other fields in the certificate, especially the common name of the certificate. So in my example, I used an email address, adventure@applehour.net. Now Caddy and Nginx will both pass along the validated certificate name to the backend if you configure them to. So you could configure that to be like a proxy authenticated user, and then any user that logs in with Mutual TLS gets sent straight to the backend without going through Authalier or something. You could also use it just as a general gatekeeper. So like instead of using a VPN, use Mutual TLS. It's much easier on your friends and family to set up Mutual TLS. You can email them a P12, ready to go. There's a lot of ways you can deploy this, and it really reduces friction compared to setting up VPNs, at least in my experience. So hopefully you enjoyed this. If you did enjoy it, I have a Ko-fi down below if you want to donate. It's kind of like Patreon, but not monthly, just one time. If you like chatting about things like this, I have a Discord server link down below for that. If you're interested in the ProtoArch case-up, link down below for that as well. And I'll see you guys on the next adventure.